All right, we're on page 646, going to 652, and then we have an assignment on 653. Still continuing with scientific notations. We talked about last time in our introduction that this is a method to abbreviate really big or small numbers. We're going to get to activity 3 and 4. So let's start with 3. Number 1, it says a water molecule has an approximate length of 0.1 nanometers. 1 nanometer is 1 over 10 to the 7th power of a centimeter. So centimeter, think of that as like the width of a penny. So that's already pretty small. This is that much more smaller than that. So this is complete the statements and answer the question. Write your answer as a decimal. So 1 nanometer is what percentage of a centimeter? It is 0. There's gonna be a lot of zeros that you're right here. It's gonna be 6 zeros after this. 0, 0, 0, 0, 0, 0, 1. Now, when you write really big numbers, you put commas after every 3 place values. For decimals, there's no commas at all for decimals to the right of the decimal point. But what I like to do, I don't know if you notice it, is I put like a tiny gap. You don't have to do this, but this helps me keep track of triples of numbers. So yeah, you're more than welcome to do that, but if you see me kind of space it out, that's the reason why. All right, and then let's go to the next one. So we have, instead of 1 nanometer, we have 1/10 of a nanometer. Right, how much is that in centimeters? So notice how we move the decimal point, right, 1 to the left to get this right here. We're gonna also move the decimal point for this thing that's above, 1 to the left. So we're gonna have 0 point, and instead of 6 zeros, since we move this to the left, we're gonna have 7 zeros. So I'm gonna put 1, 2, 3, space, 4, 5, 6, space, 7, and then a 1. Okay, it's fine if you put all these zeros adjacent to each other. That's perfectly fine. Okay, but this is just to really express, right, how much of this is of a centimeter. So if a centimeter is the width of a penny, a nanometer is really, really small. Like, I can't even tell what place value that is. This is tens, hundreds, thousands, 10,000s, 100,000s, 100,000s. That'd be 1 millionth? Maybe 1 10 millionth? All right, moving on to C. How many centimeters long is a string of 7 water molecules? So if we have 7 altogether, let's put 7 here. Right, and we're looking at centimeters for a water molecule. We're gonna have this multiplied by that bottom number with 7 zeros. So 0, 0, 0, 0, 0, 0, 0, 1. And we're counting every 3 from the decimal point, whether that be to the right or to the left. And if you multiply this, you're gonna get 0 point, same amount of zeros. And then instead of a 1, 7 times 1 is just going to be 7, right? Because 7 times 0 is just 0. So a really, really small number. I think this is 7 over 7 10 millionths. Really small. So that's a water molecule. All right. So it says just as large numbers, just as with large numbers, you can use scientific notation to express really small numbers. By counting zeros, the value of the number does not change, only its form. We're going to analyze these people's representations here. So we have Brock, and then on the next page, Corinne and Kanye. So we're going to have Brock here. How do they represent? So you can start with 6.5, which is less than 10, right, and greater than 1. It's in between 1 and 10. But I divide by 10 and I get 0.65. When I divide by 10 again, I get 0.065. You could just keep dividing by 10, and we notice, right, what happens here is that that decimal is moving. Divided by 4 times, so 0.00065 is this fraction. But in scientific notation, we had to use multiplication, not division. That's okay, because 6.5 divided by 10 to the 4th is the same as 6.5 times 10 to the 1 over 10 to the 4th. And since 10 to the 4th or sorry, 1 over 10 to the fourth, you can write this as a negative exponent. Typically, we don't want to write as a negative exponent, but it's fine in scientific notation. We prefer not to have that fraction. This would be equal to 6.5 times 10 to the negative fourth. Okay, moving on to the next page. All right, so Karine decided to write the number as a fraction less than 1. 65 over 10, or sorry, 100,000. If I divide both the numerator and denominator by 10, we'll get this new fraction. And as a power of 10, I can write the number of 10,000 as 10 to the fourth power. Yep, it has 4 zeros. So that 6.5 divided by 10 to the fourth, which is the same as 6.5 times 10 to the, or sorry, 1 over 10 to the fourth, which is as a negative exponent right here. Okay. Right, so simplifying the numerator and denominator, that was Karine's method, and then converting that fraction into a negative exponent. And then Kanye, I moved the decimal point in the number to the right until I made a number greater than 1 but less than 10. So I moved the decimal point 4 times to make 6.5, and since I moved the decimal point 4 times to the right, that is the same as multiplying. You got to be careful here. Right, 10 times 10 times 10 times 10, or 10 to the fourth. So the answer should be 6.5 times 10 to the fourth. Okay. Number 2. Explain what is wrong with Kanye's method. So notice the differences between this, and we're looking right over here. Kanye's exponent, right? There is a 4 involved, but it should be the exponent should be negative. Right, because since we have a positive, that's actually a really big number rather than a really small number. So positive exponent indicates a large number, whereas he works with a small number. And do you prefer Brock's or Karine's method? I mean, this is up to you. But I'm gonna say I like Brock's method here. I'm just gonna put Brock's method. You can count the number of times I need to divide. Right, we're looking at tens by moving the decimal place. Right, so we want to think of multiplying by 10 or dividing by 10 by it's moving that decimal place every single time. Okay, let's go to 648. All right. So we have this table that is representing, looks like the metric system. Measurements smaller than a meter, M, have their own names. These statements show how some small measurements relate to a meter. So a centimeter is 1 over 10 to the second. So that's 1 over 10 to the second is 100. So 1/100th. I'll just write it like this, just so you can. So to express how small that is, it means, 1 over 100. 100 centimeters makes 1 meter, or that a meter is 1/100th of that. So you would need a lot for that. Like for millimeter, this would be 1 over 1,000. So it would take 1,000 millimeters to make a meter, and a meter is like slightly bigger than a yardstick, so like slightly longer than your waist. It's kind of like the height of from the ground to like a doorknob. That's typically a meter. All right. We're going to convert each measurement to meters and write each measurement as a power of 10. Okay. So 1 meter. Right, this is using the first one. So, 1 centimeter, right over here. It's 1 over 10 to the 1 over 10 to the second, which is just 10 to the negative second. So this is in terms of meters. Right, 1 millimeter. This is 1 over 10 to the third power. We could write this as just 10 to the negative third power in terms of meters. Micrometer, 10 to the negative 6 meters. Nanometer right here, that'll be 10 to the negative 9th meter. And a picometer, that's a new word for me, 10 to the negative 12th power in terms of meters. Okay. All right, so moving on to this next part, we're number 5. It says write the radius of each type of blood vessel in standard form. So they're written in scientific notation. It says the capillary is one of the minute blood vessels that connect arterioles, and venules. Ooh, have your science teacher help me with these words. Anyways, so we have this written as 5 times 10 to the negative third. What I'm going to do is I'm going to write 5, right? I'm going to write that A value. If you don't know where the decimal is at, it's always at the end of a number if it doesn't appear. And this negative 3 tells me to divide this 3 times rather than multiply it 3 times, or it also tells me to move it 3 to the left. So 1, 2, 3 to the left. So this is 0.005. I always put a 0 here. There's always kind of a 0 before the decimal point. You don't have to put that initial 0, but the radius of a capillary is 0.005, and this is in terms of millimeters. All right, next one. I'm going to ignore the context. I'm just going to go right here. 1 times 10 to the negative second, so decimal point is right here. Negative 2 tells me to move 2 to the left. So 0.01 millimeters. Or to clean this up, I'll write it like this. And C, arteriole. The arteriole is a small blood vessel that extends and branches out from an artery and leads to capillaries. Interesting. Okay, I'm gonna write that A value again, and this is saying move it -1, so I move it 1 to the left. So you could write this as 0.5. You could put 0, but that would be 50 hundredths, and 50 hundredths is the same thing as 5 tenths. 50 pennies is the same thing as 5 dimes. So you could put it, I'll write both. I'll write both. These two things are the same thing. All right, smaller than a millimeter. Okay, going on to the next page, number 6. Convert each measurement to meters, and then write the answer in scientific notation. So now we're going from the other way. Going from standard form. A standard form is just a way a number is just typically written. Okay. We're going to have to use the other pages because we have, in terms of differing units here, nanometers, micrometers, nanometers again, picometers. Okay. We're just going to do 2 of these. We'll do A and C. I'll leave B and D as you do. So the diameter of a water molecule is 0.29. 0.29 nanometers. So we look over here, nanometers. All right, that was at that's 10 negative 9th power. So we could write this as 0.29 times 10 to the negative 9th power. This is in terms of nanometers, but this is not written in scientific notation. The reason is because this number is not between 1 and 10. Right? Think of this as 29 cents. 29 cents is not between $1 and $10. So we have to move this decimal point, and this is just our decimal here. We have to move it, that decimal point, so where the decimal gives us a number between 9 and 10. And if I move that decimal point 1 to the right, this gives us, instead of 0.29, it gives us 2.9. That's what we want, times 10. Since I'm moving this to the right here, this tells me that I have to take that exponent and decrease it. So think of like going down 9 floors for this -9. I'm going to go down another floor, making it -10. So this is the correct answer here. All right, great. Let's move to the next one. So the diameter of a red blood, letter C, 7 nanometers. Oh, so I'm going to put 7. Nanometers is actually what we just did for A, so it is times 10 to the negative 9th power. This is actually already written in scientific notation because 7 is in between 1 and 1 and 10. That is good. We're done. Okay. All right, moving on to completing the table. So take this time to complete the other parts. We have various objects. We have the Earth, radius in terms of meters. So how many like meters does it take from the center of the Earth to the edge of the Earth? It's a lot. Brachiosaurus, we're talking about mass in terms of kilograms. Dust mites. So dust mites are really small. Length in meters. And the nucleus of an atom. Nucleus of an atom. So an atom's really small. Nucleus is just a part of that. So that's also really, really small. Okay. I'm going to leave. We're going to do some parts together, some parts you do. We'll do this one together, and we'll do this one together. Actually, we'll do this one because I want to go over a small one to give you an example. All right. So we have standard form that's missing on the first one, but we do have science notation. If it's positive, we're going to move this to the right. So this is going to go 1, 2, 3, 4, 5, 6. I know there's stuff in the way, but we're going to put zeros in place of that. So this would be 6, 3, 8. Looks like there's going to be 4 zeros. From the end of the number, we're going to count every 3. Commas have nothing to do with the decimal point. The decimal point is technically right here, but you don't typically see it, so I'm going to get rid of it. All right, next one. Now we have, this is the dust mite. We have the decimal here, but you want the decimal in a place where this entire number is in between 1 and 10. Where that becomes is right over here. If I put that decimal point after what we call the first non-zero digit, that just means first digit that's not a 0, always to the right of it. So I'm going to count how many spaces I move that way. 1, 2, 3, 4. I'll put an arrowhead. This was 4 to the right. Now, this will be 4.2 times 10 to the -4th. Okay. Now, why is this negative? The reason that we know that this is negative is because this number is smaller than 1. Sorry, this entire number right here is smaller than 1. Really, really small. Really small numbers are negative. Really big numbers are positive. But also, this is telling us that if we were to take this right here and move that 4 to the left, 1, 2, 3, 4, we would get this number right over here. Okay, so it's kind of like moving in the opposite direction. I know some students think of like, oh, since we move to the right 4, that's +4 because they think of a number line. You can only think of a number line when you go from scientific to standard form. Going from standard form to scientific, you're kind of working the opposite direction. It's like you're retracing your steps. So just be careful with that. Work on the other ones and let me check that. All right, moving to 650. Okay, so 650, we are comparing just various numbers using either, we can't confuse these, this is greater than, this is less than, and we're already familiar with equal to, okay. Okay. Now, when you look at numbers like this, it's somewhat easier to compare because they have the same exponent, right? Here we have 10 to the 4th. We also have a 10 to the 4th. So really just comparing that first value here, right? Which one is bigger, 4.5 or 1.5? 4.5 is bigger. We're going to write this, which means the right side is greater than the left side. All right, moving on to B, right? Do they have the same exponent? Yep. Okay. So 8.1 is greater than 7.6, or we could say 7.6 is less than 8.1. Okay. Now it is at this one right here, we have different exponents. We have a 4, we have a 7. Okay. Now this is 4.5 and this is also 4.5. So I know it starts out with 4.5 something. I'm not going to do this for all the problems, but we're going to do it for this one. We're going to have 4.5, but I'm going to move this 4 to the right. 1, 2, 3, 4. This number is, I'm going to put a comma there, is 45,000. Okay. If we do this as well, move it 7. 1, 2, 3, 4, 5, 6, 7. It's got to be in the millions at least. 1, 2, 3. So that is 45 million. So 45,000, 45 million, 45,000 is definitely less than. Now, we didn't have to write it in standard form, but just to prove it, I did want to. Okay, which one do we think? D or, so for D, I'd like for you to complete this as a you do. I'd like for you to pause here, you write the symbols, but I'm gonna put the answers in like 2 seconds. Okay. So hopefully you've paused. I'm just gonna write the answer. This should be greater than, this should be less than, this should be greater than. Okay. But if you're not sure, expand it out, just like what we did with C, so you can see how to compare. Number 2, explain how to compare two large numbers using scientific notation. All right, so what do we do? When comparing two numbers in scientific notation, first compare the characteristic. So compare the characteristic. Now, the characteristic, if you remember from the last lesson, that is the exponent. They just call it the characteristic though. A larger characteristic indicates larger number. When the characteristics are the same though, then we look at the, I've been calling it the A number, but it's the mantissa. So that is really the coefficient. So I'm going to put that is the A number in terms of A times 10 to the B power, where coefficient is B, mantissa is A. So we go in that order. Okay, the greater the mantissa, the greater the number. All right, great. Okay, now it looks like we're working with really small numbers here. So with this, let's look at the mantissa. Or sorry, let's look at the characteristic, the exponent. All right, 4.5 is greater than 1.5. So with this though, so we're gonna say this is greater than, or we're not talking about negative numbers here, even though we have a negative exponent. So just to understand this, 4.5, we're gonna move this 4 to the left. 1, 2, 3, 4. And this right here, we're gonna put 1.5. We're gonna move this 4 to the left. 1, 2, 3, 4. All right. What is this? Tens, hundreds, thousands, 10,000s, hundreds, thousands. So this is 4,500 thousandths, and this is 1,500 thousandths. 45 of something is definitely going to be greater than 15 of something. Okay. All right. Next one. This one is less than, because they have the same characteristic. We compare 7.6 and 8.1. All right. C. Now we're looking at the mantissa, because, hold on. Right, your exponents are different. Oh, sorry, we're looking at the characters because the mantissas are the same. So 4.5 and a 4.5, but this is -4, moving it 4 to the left, and -7, moving it 7 to the left. This will be greater than, number off to the right, okay? And just like we did for the other ones, pause it at this point. I'd like for you to try it, and then play it to determine what are the inequalities. It looks like we don't have any equal to. So it's either gonna be less than or greater than. Answers. This is less than, greater than, and this one is less than. All right. Number 4, explain how to compare two small numbers using scientific notation. It's the same thing. We're gonna look at the, I'm gonna abbreviate mantissa, I'll just put M-A-N-T, and characteristic, I'll just abbreviate there. All right, let's go to skip number 5. We pretty much already talked about that. Okay. All right, we're gonna do a little bit of talk the talk. We're just describing a definition of scientific notation and an example. So scientific notation is a way to express a number as a product. So we're specifically using multiplication of a number between 1 and 10 All right, so it's a way to abbreviate. I think that's how you spell abbreviate. So like an example could be 3.87 times 10 to the 7th power. Yep, that 3.87 is in between 1 and 10. And we have it as some type of characteristic or exponent to the 10th power. And then standard form, it's the traditional way. Traditional way of writing numbers. Or how we used to writing numbers. So an example, I'm gonna give you a big number. Let's say 59,325,123. Okay, there you go. All right, so that leaves us to our assignment. We're completing number 1, which is what you're determining whether it's in scientific notation written correctly, and if it's not, write it in scientific notation. Number 2, converting between standard and scientific form. And then 3, and then number 4. We're gonna cross off number 5. Or we could do number 5 for, we could do extra credit. Anyways, we'll leave it at that. So this is page 653, numbers 1 through 4.